Hello friends, welcome to follow up. In this video, we are going to look at today's daily challenge problem 662, maximum width of a binary tree. In this video, we are going to explain a solution based on traversal. We are going to explain a solution using recursion. First, the problem asks us to return the maximum width of a given binary tree. So here, the maximum width of a tree is the maximum width among all levels, and then it defines the width of a level. So this is defined as the length between the end nodes. In other words, the leftmost and the rightmost non-null nodes. So this is an important assumption here, null, right? So here the null nodes between the end nodes that would be present in a complete binary tree extending down to that level are also counted in the length calculation, right? So it's guaranteed that the answer will in the range of a 32-bit signed integer. So here it's important to digest this paragraph. Basically, it defines the width of a level. So if we find the width, if we can find the width of each level, and then we just need to use a running variable to get the maximum one. So that will be the general logic. So let's look at the examples here. So in example 1, so here the return is 4, because here if we have one null, so this will be the third one, right? So this is the fourth one. So we have 4 in this example. And in the second example, we're going to have 7, right? So if it's complete, so this node, if the right child of the node 9 will be the 8th node in this level, and 7 is the 7th, right? So we're going to return 7. So in example 3, the return is 2, because the maximal width is occurring at the first level, right? So here 3 and 2, right? So this level actually is complete. So actually this from this output, we haven't touched the core point of the computation of width for each level. So basically the core for getting the width is the indexing, the node indexing in a binary tree. So we are going to explain in a minute. So before we move to the analysis, let's look at the constraints. First, the number of nodes in the tree is given in the closed interval with two ends, 1 and 3000. So this number is not very large, right? But you know, if the binary tree is good, so it can have a very deep level, right? So for example, we have 2999, right? In other words, 3000 minus 1 levels or length in the from the root to the leaf, right? So here the node value is in between 100, negative 100, and positive 100. So this is not that essential, because we are not interested in the specific value. Meanwhile, the value are also non-unique, because we have more nodes. We can have more nodes, but we have only 201 different values in this range, right? So with that said, we are ready to do the analysis. So here the point we're going to solve this problem is going to based on traversal algorithm, right? So for this problem, it's best it's maybe might be a good idea to use level order traversal, because for each level we're going to get the width. So in this problem, first let's make an observation, because from here, if you just look at the output, it might be not obviously for beginners. So how to compute the width? So the width of a level actually equals the index difference plus 1. So here the index difference is the difference between the leftmost and the rightmost nodes in the same level, in this level, right? So basically, once we realize this observation, so it's very easy to interpret the output. However, we need to make a convention on the indexing. So for indexing of nodes in binary tree. So here there are two options, right? So option 1. So if we use zero indexing, right? So assume that we have a parent. The parent have an index p, right? Then the two nodes, the left and right children, if have, right, will have index. So 2 times p plus 1 and 2 times p plus 2. So this is one option. So another option, let me copy this line and right here, option 2. So we use one indexing. So if we use one indexing, so we just need to adjust here. So 2 times p plus 2p plus 1 for the left and the right children. So if we can look at this example, right? So just to use example 2, so to give a demonstration. So the node 1. So in this example, all the nodes have different values. So this is just for demonstration purpose, I guess. So the node 1 have index 0, right? Let's call it IDX 0. And then 3 will have index 2 times 0 plus 1, that is 1. And 2 will have index 2, right? So the width for this level is 2 minus 1 plus 1. That will be 2, right? So now if we look at 5, right? So 5 is the left child of 3, right? So the index will be 2 times 1 plus 1. That will be 3, right? And 9 is the right child of 2, right? 2 have index is 2. So 2 times 2 plus 2, that is 6, right? So the width for this level is 6 minus 3. 6 minus 3 plus 1, that is 4, right? So similarly, we can look at the last level. So for last level, 6. So 6 is the left child of 5. So 5 have index 3. So 6 have index 3 times 2 plus 1, that is 7. And 7 have index. So 7 is the left child of 9. But 9 have index 6. So 7 has an index 6 times 2 plus 1, that is 13, right? So if we compute the width for this one is 13 minus 7 plus 1, that is 7, right? So this is among there's 4 levels. Actually, the first level, just the root itself, is just 1, right? So we have we have width 1, 2, and 4, right? And 7. So we're going to return 7. So this is the interpretation for this this example. You can analyze using also using one indexing, the same thing. So basically, that's the logic for this problem. So once we could digest the reading or indexing part, so this problem is rather straightforward. So now I guess we are ready to look at the coding part. So I'm going to use level order traversal. So I'm going to compute a level. So here for each level, I'm going to associate the node with its indexing. So I'm going to use 0 indexing, right? You can use 1 indexing, it does not matter. And then let's do level order traversal. Well, level, what we're going to do. So first, I'm going to let's also initialize a width variable. So we're going to initialize using 1, because here the number of nodes is at least 1. In other words, the tree is not null tree, so the width is at least 1. So here, what we are going to do in this stage, we're going to update the stage, right? It's going to be the previous stage width and the current level and the width. So this is actually easy. So this level, the rightmost, that will be -1. Its indexing minus the leftmost, that's level 0. Its indexing, right? And then we plus 1. So after we get the level and make a comparison of its width with the width variable, then we're going to update the level, right? So for that, let's use a for loop rather than comprehension here. So for node and idx in level, then we're going to first check node left, right? If node left, so then we're going to append the information for node left. So we are going to have node left, and then the idx for node left will be the parent's idx times 2 plus 1. That is 2 times idx plus 1, right? And then we're going to check right, right? If right, then we're going to do this appending operation. So here, let's change this left to be right, and then change this plus 1 to be plus 2. And then after that, we finished computing the current level. Then we are going to reset the level to be temp, right? So after we exit this while loop, we computed all the widths for the different levels and make a comparison with the variable width. This way we get the maximum, right? So this will be the maximum width of the binary tree. So we just need to return the width. So this short code forms a solution format to this daily challenge problem. So before we make any comments, let's first do a check. Yeah, it passes the first example, I guess. So now let's look at the generic case. Yeah, it passes the generic case. I guess that's about it for this problem. So you can modify the code or think up other formats of solutions. So roughly the idea will carry out to different representations. So with that said, I guess that's about it for this video. Thank you.